In our abstraction of the polling process, we have now come upon the following question. We have a sequence of Bernoulli trials, x1 through xn, which represent random samples from an underlying environment. We form the accumulated number of successes, S sub n, and we anticipate that the fraction S sub n over n may perhaps, if you're good and lucky and say our prayers at night, represent the underlying unknown population proportion p. Now, to begin to make progress in analyzing whether this in fact is the case, we should start by understanding the nature of the chance variable S sub n, the accumulated number of successes. It is wise in such a setting to follow the Hungarian mathematician George Polier's sage advice that we should begin with the simplest version of the problem that we don't quite understand. Accordingly, let us consider the following setting. Let us begin by looking at a setting where we have a sample of size 3. In other words, we look at 3 Bernoulli trials, 3 coin flips, whose outcomes are x1, x2, and x3. The coin has got a bias p towards success, but p is fixed, but at the back of our mind we keep in mind that in the polling application p is not known a priori. Now, we have a chance experiment, 3 flips of a coin. What is a sample space? Well, by now we are quite familiar with how to write down a sample space in such a setting. To completely articulate the sample space, we're going to have to write down all possible strings of length 3 of zeros and ones. There are 8 possible strings arranged from left to right in order of first through third. What are the probabilities we want to assign to each of these atoms? Well, here's where independent selection comes into play. Chances multiply under independent selection. We actually have a product space here, a space of repeated independent trials. The success probability is P, the failure probability is Q. So the chance of obtaining 3 failures in a row, 3 zeros, is Q times Q times Q, or Q cubed. The chance of obtaining 2 failures to begin with, followed by a success, is Q times P, or Q squared P. The chance of obtaining a failure, a success, and then a failure is Q times Q, or Q squared P, and so on. Of course, we are very familiar now with this kind of setting. We promptly take this raw data and assemble it to form the accumulated successes in our sequence, x1 plus x2 plus x3, what we've called S sub 3. And of course, S3 is now a new chance variable. It inherits certain atomic probabilities. What is the chance that S3, the accumulated sum of 3 tosses, is k? Now, hitherto we've used p of k for the atomic function, but p is overloaded here. We are using p here for the success probability of a coin. So let's introduce some new notation. Let's call this b for Bernoulli of k. So b of k represents the probability that the accumulated sum of 3 Bernoulli trials takes value k. We now have a new chance experiment. We've got a new sample space engendered by these sums. What are the possible values for S3? Well, this is easy enough. Since S3 is a sum of 3 zeros and ones, the outcome can only be 0, 1, 2, or 3. And therefore, we can think of this metaphorically as a new chance experiment, where we are throwing a 4-sided object. And the object has got faces 0, 1, 2, and 3 with certain weights or atomic probabilities. Our job now is to figure out what these atomic probabilities B0, B1, B2, and B3 are. Let's take, for example, the case where the sum is 1. How can the sum of 3 zeros and ones be 1? Well, it's very clear that by an inspection of the possibilities, this can only happen if there are precisely 2 failures and 1 success, 2 zeros and a 1 somewhere in the sequence. And inspection shows that this can only be the case if the outcome of the original experiment is 0, 0, 1, 0, 1, 0, or 1, 0, 0. What is the probability we want to associate then with the accumulated sum being 1? Well, naturally enough, we add the various atomic probabilities. But we notice that each of these atomic probabilities is exactly the same. 2 failures and a success in any order has got probability q squared p, and therefore the ensemble possibility is thrice q squared p. Right? And we now put this all together. So B1 in our setting is thrice q squared p. What about B0? Well, that corresponds to S3 being 0. This can only happen if all 3 of the trials result in failures, and therefore the probability is q times q times q, or q cubed, and so on. Now we see how we can build these probabilities by consideration of the individual sequences and careful reassembly of sequences which belong together. Well, this idea generalizes very, very quickly, and so without further ado, let's consider the general setting. So let us begin now with a sample of a generic size n. x1 through xn represent Bernoulli trials by tossing your coin with success probability p. Let S sub n represent the accumulated successes in these n trials. Our question is to figure out what the distribution or the atomic mass function there is that we should associate with S sub n. Now, let's consider a particular sequence. In this case, let's say we're looking at a sequence of 12 trials. I've color-coded as before, 0 by blue, 1 by orange, and we've got a particular sequence. 12 trials, of which exactly 4 are 1, 4 are orange. What is the probability, the atomic probability, in the space of these Bernoulli trials of observing such a sequence? Of course, here's where independent selection comes in and simplifies matters for us. Probabilities simply multiply. And so, reading from left to right, I multiply probabilities q times p times p times 4 q's times p times 2 more q's, then a p, then a q. Or in other words, there are exactly 4 p's in the product and 12 minus 4, or 8 q's in the product. And so, the probability of observing this particular sequence of 4 successes in 12 trials is p to the power 4 times q to the power 12 minus 4. And now we come to the key idea. What is the chance of observing some sequence with exactly 4 successes? Now, a little introspection tells us, well, the picture is going to be a lot like the one we have on the screen, with the proviso that the 4 orange balls could migrate and move around. But at the end of the day, we're going to have 12 balls, of which precisely 4 are orange. Every sequence, every atom that contributes to the event that there are exactly 4 successes will have probability p to the power 4 times q to the power 12 minus 4. And so the question now is, how many such sequences can we construct? This now is a purely combinatorial problem. And of course, we are very familiar with this. And if the listener thinks back to the preview lectures on combinatorics, in particular Tableau 3 Part 2, we realize, oh, this is given by a binomial coefficient. The number of ways in which we can select 4 positions out of 12 is 12 choose 4. And therefore, the probability of observing exactly 4 successes in 12 trials is 12 choose 4 times p to the power 4 times q to the power 12 minus 4. And now we've understood the basic principle. What we want to observe k successes. Well, our first line will be replaced by a particular sequence with k successes, and of course n minus k failures, will have probability p to the power k times q to the power n minus k. What is the probability of observing exactly k successes in those n trials? Well, those k successes must be distributed somewhere in n positions. There are n choose k ways of selecting them, and therefore the probability at hand is n choose k times p to the power k times q to the power n minus k. Simple. Now, a little notational grease will make our steps forward a little bit easier. Of course, these probabilities are exactly the probabilities, the atomic probabilities for the accumulated successes. This is what we called B of k. But we should keep at the back of our mind that k is the free variable here, counting the number of successes. But we are parametrized by two additional variables which are the backbone of the problem. N, the number of trials, and P, the success probability of the coin. So these two parameters, N and P, parameterize an underlying probability law as k varies between 0, 1, 2, 3 up till n. The number of successes in n trials can only be an integer between 0 and n. Now, let's very quickly summarize our discovery. We have discovered the august binomial distribution. We started with variables corresponding to independent sampling from an underlying distribution. In this case, the simplest of distributions, a Bernoulli trial, a coin flip. x1 through xn are Bernoulli trials. The underlying sample space is strings of zeros and ones of length n. Of course, independent selection makes the description easy. S sub n is the accumulated number of successes. We will say it has the binomial distribution because of the appearance of the binomial coefficient in its formulation. And this distribution, this atomic probability law, is parameterized by two parameters, the number of trials n and the success probability p. So k is your free variable. K is going to run between 0 and n. And for every choice of n and every choice of p, we've got a new binomial distribution. Right? The word distribution here is a surrogate for the atomic mass function for this particular problem. What we've discovered is a new chance variable, the accumulated successes, contrived, put together from these old variables x1 through xn. At this stage, before we proceed, we should consider whether we've done our calculations correctly. After all, the B of k, as k varies between 0 and n, is purportedly an atomic mass function. And of course, this engenders a probability measure on the underlying space, which now I can think of as just the numbers from 0 through n. Is this in fact a bona fide mass function? Have we done our calculations correctly? Of course, we could say, look, clearly we have done our calculations properly, in which case this must be the right answer, and therefore the BKs must be bona fide, which means that they must be positive and they must add to 1. But of course it is always wise to double-check our calculations. Let us begin by checking positivity. But of course, this is trite. The binomial coefficients are positive, by definition, and P and Q are positive, and therefore the binomial probabilities Bn of k and p are going to be positive. So positivity is trite. What about normalization? Well, we require these probabilities to add to 1. Well, let's check. The sum of these binomial probabilities gives you an expression, a sum, but a little introspection tells us that looks complex, but it's actually very familiar. The sum in the middle is exactly the binomial expansion of p plus q to the power n. But recall that q is 1 minus p, or in other words, p plus q is exactly 1. And therefore, 1 to the power n is manifestly 1, and therefore indeed the sum of the binomial probabilities adds to 1 as it must. The listener will recall that we've gone through this calculation in a less intuitive setting in Tableau 6 Part 1, when we were looking at examples of mass functions, and we just pulled this one out of our hat. And it worked out. But now we understand where the setting is. This arises any time we consider sequences of coin tosses and we consider polling applications. Now we've got a bona fide distribution at hand, a bona fide atomic mass function on this space of accumulated successes 0, 1, 2, 3 up to n. Before we proceed further, it is always wise to examine the structure to see whether we can glean some more information from it. In the wise words of the Hungarian mathematician George Polya once again, Polya recommends that we draw a picture. And so let us draw a picture without further ado. Let us focus on the case where n is 100 for definiteness. So we pick a suitably large number which is not so small that it is trivial, and plot the binomial probabilities for different values of p. So on your figure you now see 3 cases, p being 0.3, p being 0.5, that is a fair coin, and p being 0.8. And you can see the binomial probabilities already have got certain nice symmetries, certain clean characteristics which are tempting to analyze and which suggest that there are simplicities waiting for us to discover. So, for example, it seems clear that the binomial probabilities are unimodal. They increase smoothly and they decrease smoothly. It seems clear that the binomial probabilities march to the right as p increases. A little introspection will convince us that this is in fact to be expected, though of course intuition by itself would not tell us the precise nature of how quantitatively these probabilities behave. The pictures suggest also that there is a centering phenomenon going on. When the coin is fair, p is 0.5, we find that the maximum value, the center of these atomic mass functions, the distribution, arises at the halfway point, 100 divided by 2. When p is 0.3, the center appears to be 0.3 of 100, or at about 30. And when p is 0.8, the center appears to be at about 0.8 times 100, or at 80. Accidental? Certainly not. But of course, this is going to require some more discovery. Something else can be gleaned. As p moves away from 0.5, the curves get narrower. In other words, there appears to be maximal uncertainty when the coin is fair. And as p moves towards 0 on one side or 1 on the other, the curves get narrower and narrower, which means there is more and more certainty. Again, very intuitive, because when a coin is very heavily biased towards 1, you would expect a lot of 1s. You'd expect a big accumulated sum. And similarly, when a coin is very biased towards 0. But again, the picture tells us there's not just a qualitative understanding, but it suggests that there's a quantitative description lying in wait to be discovered. But we are getting ahead of ourselves. This gives us enough to understand the nature of the distribution of accumulated sums. We should pause now and promptly try to settle our intuition by looking at simple examples. So this comes up next.